Last week we were talking about solving systems of linear equations. Today we're going to put it, or this week we're going to put it together and talk about linear programming, which deals with 3, 4, 5 different inequalities coming together to form a solution to a problem, usually a business problem. Many applications in business and economics involve a process called optimization, in which you find the minimum or maximum value of a quantity. In this section, we will study an optimization strategy called linear programming. A two-dimensional linear programming problem consists of a linear objective function and a system of linear inequalities called constraints. The objective function gives the quantity to be maximized or minimized, and the constraints determine the set of feasible solutions. For instance, suppose you want to maximize the value of z is equal to ax plus by. That's our objective function, subject to a set of constraints that determines the shaded region shown at the right. So this is my shaded region, and this is my objective function. Now, somebody came up with this a long time ago. It said that the maximum or minimum value of a shaded region has to occur at one of the corner points. So that means, and obviously all of these points in the shaded region are solutions to this function, but they are not going to be the maximum or minimum value of the function. That has to occur at the corner point. So that really makes it easy when finding the maximization of a problem like this. Because every point in the shaded region satisfies each constraint, it is not clear how you should find the point that yields a maximum value of z. Fortunately, it can be shown that when there is an optimal solution, it must occur at one of the vertices or corner points. This means that to find the maximum value of z, all we have to do is test each of the corner points. The guidelines for solving a linear programming problem in 2 variables are listed below. Step 1, sketch the region corresponding to the system of constraints. The points inside or on the boundary of the region are feasible solutions. Find the vertices of the region. Test the objective function at each of the vertices and select the values of the variables that optimize the objective function. All right, so let's do an example. So here it gives us, it says find the maximum value of z, and usually what they do is, most of these are business problems, so usually this is called the profit function. So let's say that this is the profit is equal to 3x plus 2y, subject to the following constraints. X is greater than or equal to 0, y is greater than or equal to 0. Now these 2 constraints are always 2 constraints that we use when we're dealing with linear programming problems, because it makes sure that our answer is always in the first quadrant, which makes it positive. And then x plus 2y is less than 4, and x minus y is less than 1. Okay, so the first thing what we're going to do is we're going to graph these constraints out. Okay, and then we're going to find the corner points. All right, so, and again, our profit function is equal to, it was, I think it was 2x, no, it was 3x plus 2y. Okay, so our profit is equal to 3x plus 2y. Okay, so now we've graphed this out. X is greater than 0 would be this line, y is greater than 0 would be this line, x plus 2y is equal to 4. So we have a couple of corner points. We have 0, 2 is a corner point. 0, 0 is a corner point. 1, 0 is a corner point. 2, 1 is a corner point. So these are the only values that we have to check out in our profit. So if I put this into my profit function, if I put 0 in for x and 2 in for y, so that gives me 4 here. 0, 0 would lead me, and doesn't that make sense? If this is a production and you make 0 of anything, your profit is going to be 0. And then 1, 0, so that would give me 3 here, and then 2, 1, so that would give me 3 times 2 is 6 plus 2, so that's going to be 8. So my maximum value or my maximum profit would be to make 2 of whatever the x's and 1 of the y's, and that would give me my maximum profit. So this is what we're going to be doing this week. So you're going to come up with your constraints, your profit function. and then you're going to plug them back in to the profit. You're going to find the corner points, plug them back into the profit, see which one leads to the largest profit. So, and they did that over here. So the maximum is going to be 8. Okay, and then they took a bunch of points that were in the shaded in region, and they showed that none of them, is larger than 8. So the corner points definitely are. So an application. This is a candy manufacturer wants to maximize the combined profit of 2 types of boxes of chocolates. A box of chocolate covered creams yields a profit of $1.50 per box, and a box of chocolate covered nuts yields a profit of $2 per box. So if I was going to make my profit function up, because I know what the profit is, right? So I just have to let's say that the covered creams are X and the chocolate covered nuts are Y. So my profit function is going to be $1.50 for every box of creams I make, plus $2 for every box of chocolate covered nuts I make. So this would be my profit function. We do not graph the profit function. That is not part of our graph. Okay, and then they'll give you some constraints. The combined production level should not exceed 1,200 boxes per month. So I would go X plus Y is less than or equal to 1,200. That would be a constraint, and I'd have to graph that out. The demand for a box of chocolate covered nuts is no more than half the demand for a box of chocolate covered cream. So I'd have to write out a constraint for that, and I'd have to graph that also. So those are the types of constraint problems that you would have on there. So let's take a look at a problem where you do have to write out your constraints. And usually in a problem like this, you should always have X is greater than 0, Y is greater than 0. That should always be constraints on a problem like this. Okay, so in this problem, it says a drama club is having a car wash as a fundraiser. They wash X cars at $5 each and Y cars at $8 each. Okay, so right away, I'm just going to write down 5X plus 8Y. They will wash at least 26 cars. So right away, I know that at least, so X is greater than or equal to 26 and 15 trucks. So Y is greater than or equal to 15. So they have to wash at least that many. They need to make at least $250. Okay, so 5X plus 8Y has to be greater than or equal to $250. So that is another constraint. Which system describes this situation? Okay, so I'm looking at my 3 constraints here. X is, well, that's not right. X is greater than 26. That's I wonder if that one of those, they have both Y's there, so I'm going to cross that one out. X is greater than 26. Y is greater than 15. 5X plus 8Y is less than or equal to 250. Now they want to make more than that, so I'm going to go to this one. Greater than 250. So that's how you're going to come up with your constraints, and then your next step would be to graph it out and see which one gives you the best profit. Here's another example. It says a factory makes widgets and gadgets. Widgets cost $3 and gadgets cost $5 each to make. Okay, so that's how much it costs to make them. So I've got X, or 3X plus 5Y, and pretty soon they're probably going to tell me how much money they have. It says the total cost needed to be at most $300 per day. So this has to be less than or equal to 300 because I can't spend more than $300 a day to make widgets and gadgets. And it costs $3 to make a widget and $5 to make a gadget. So the boss wants at least 10 widgets. Okay, so X has to be greater than or equal to 10. And 20 gadgets, so Y has got to be greater than or equal to 20 per day. What system represents this situation? All right, so I'm looking at this. 3X plus 5Y is less than, okay, that looks good. X is greater than 10, Y is greater. I'm looking at letter C. Looks pretty good to me.